There is this incredibly specific, almost cinematic moment in almost every software engineering interview.
Oh, I know exactly the moment you mean.
Right. The room gets perfectly quiet. The interviewer leans back. Maybe they slide a blank laptop across the table to you, or they just gesture to this completely untouched whiteboard.
It's terrifying.
It really is. And then they give you a prompt that sounds deceptively simple. They look you directly in the eye and say, find the top 10 items in this list.
It sounds so innocent, doesn't it? Just 10 little items.
Exactly.
But it's a trap.
It is entirely a trap. Top case selection is essentially the main character of technical interview questions, and people fail it all the time, not because they lack coding skills, but actually because they are entirely too good at memorizing heaps.
Which is fascinating.
Yeah.
And that is our mission for this deep dive. We are pulling from a stack of system design interview guides, engineering blogs from high-scale tech companies, and several really dense computer science papers on hardware-level algorithm optimization. Oh, the hardware papers are so good. There is something incredibly satisfying about getting down to the bare metal.
Yes, absolutely. We want to use those sources to explore why this one simple-sounding question is actually an entire family of complex problems just masquerading as an easy prompt.
Because when candidates here find the top 10 items, their brain instantly triggers a reflex. It's like muscle memory.
Right. They mentally shout, Min-Heap, O of n log k, give me my offer letter.
Exactly. They think they've nailed it.
But real engineering, as we've talked about before, is basically the art of being annoyed by constraints. Okay, let's unpack this. If you jump straight into a heap without asking about the underlying data, you are basically trying to use a surgical scalpel to mow a lawn.
I love that analogy so much. It's perfect.
Right, because a scalpel is exceptionally sharp. It's precise,
Right.
but its precision is totally mismatched to the volume of the task. You will literally be out in the grass all year.
And that highlights the core issue perfectly. Precision versus volume. Interviewers are, they're quite deliberate about this. They leave the problem completely underspecified on purpose.
They want you to stumble into the trap.
They do.
Yeah.
They aren't checking if you can write a data structure from memory. They're testing your engineering maturity. They want to see if you instinctively feel in your bones that a data set where n equals 1,000 operates under completely different physical laws than a data set where n equals 1,000,000,000.
Right. The constraints completely dictate the physics of the problem. Let's actually look at the mechanics of that default reflex, the heap approach, and see exactly where the engine starts sputtering.
Let's do it. So most people know the textbook method. You maintain a min-heap strictly of size k.
And as you scan through your n elements, you just compare each new element to the root of the heap. If it's bigger, you pop the smallest item out and push the new one in.
Exactly. That is the standard implementation, and it's elegant. It strictly bounds your memory usage to O of k space. But consider the physical mechanism of that heap when k scales up.
Right. What if k is huge?
Yes. What happens if the prompt requires finding the top 1 million records out of 10 million?
Oh, wow. So you have a heap with 1,000,000 nodes.
Right. Every single time you swap an element, the heap has to rebalance its internal tree. The new element has to bubble down. It's comparing itself to child nodes over and over and over just to maintain the heap property.
So it's that bubbling down process that absolutely kills the efficiency. That is the log k factor in the time complexity that people memorize.
Exactly.
Because when k is 10, a tree only has, 3 or 4 levels. So bubbling down takes literal microseconds.
Barely a blip.
But if k is 1,000,000, the tree is nearly 20 levels deep. That constant rebalancing, the shifting of nodes up and down the tree for every single insertion, it starts to generate serious computational friction.
And the algorithm basically begins choking on its own structural overhead. When the heap hits that ceiling, the textbook alternative that people reach for is usually QuickSelect.
QuickSelect.
Yeah, it gives you an average time complexity of O of n by partitioning the data directly. It picks a pivot, throws everything smaller to one side and everything larger to the other. It completely avoids the continuous rebalancing of a tree structure.
Let me make sure I have the mechanism right here for anyone listening who hasn't used it in a while. QuickSelect works because, unlike a full quicksort, which meticulously sorts both halves of the partition data,
Which is way too much work.
right, QuickSelect only recurses into the half where your top k elements must live. So you are throwing away half the remaining data with every single sweeping step.
That is precisely how it achieves linear time on average. You are having the problem space repeatedly. It is beautiful on paper, but it relies entirely on picking a good pivot to divide that data evenly.
And I'm guessing this is where the real-world environment punishes the textbook answer.
Oh, absolutely. What's fascinating here is that QuickSelect has a well-known, very dark side. A worst-case O of n squared time complexity.
Wait, is it always that fast, though? What's the catch when we bring this into a high-stakes production environment?
The catch is the data distribution. If you accidentally pick the absolute largest or smallest element as your pivot, you aren't throwing away half the haystack. You are just removing one single piece of hay.
Oh, I see. Because if the data is already partially sorted or has a skewed distribution, your pivot might only reduce the problem size by one element per iteration.
Exactly. You essentially end up scanning every single item against every other item. And in a live production environment, that is a ticking time bomb.
Yeah, you cannot afford a latency spike where your system suddenly runs 1,000 times slower just because the input data happened to be arranged unfavorably. That would take down a whole service.
It really would. And that brings up an even harder constraint. A latency spike on a standard processor is bad enough. But what happens when the physical hardware itself just flat out rejects the algorithm?
Oh, this is the GPU curveball.
Yes. We know that code doesn't execute in a vacuum, right? It runs on specific microchips. If we move this workload from a CPU to a GPU, for instance, both heaps and QuickSelect completely fall apart.
Because they are incredibly hard to parallelize. A standard CPU and a graphics processing unit handle workloads in fundamentally different ways.
Exactly. A standard processor is, it's like having a few incredibly smart professors. They can handle highly complex, branching, sequential logic, like a heap's constant bubbling down or QuickSelect's recursive pivoting.
But a GPU is a totally different beast.
It is. A GPU is like having 10,000 elementary school students. They aren't designed for complex individual logic, but they can execute simple, identical tasks simultaneously.
Okay, so the bottleneck with a heap on a GPU is that a heap is a centralized sequential structure.
Right.
You would have thousands of parallel threads all trying to read and write to one single root node at the exact same time. The threads just end up waiting in line, totally locked out of the memory they need.
Which totally defeats the entire purpose of having parallel processing in the first place. We've identified the exact bottleneck, and this is where we need to look at algorithms designed explicitly for parallel hardware architectures.
Here is where it gets really interesting. The sources highlight computer vision as a perfect example of this.
Oh, it's such a good example.
Imagine processing video frames, and you need to isolate the 1,000 best Harris corner scores, which are basically visual features used to track movement across a grid of 2 million pixels. And you need this done instantly, frame by frame.
You cannot use a heap. You cannot use QuickSelect. You need a completely different mental model. The sources mention Bitonic networks and radix selection.
How do those actually process data differently under the hood? I mean, how do they satisfy the GPU's architecture?
They shift the computation from a global structure to what we call warp level and block level reductions.
Warp level reductions. That sounds incredibly sci-fi.
It does. In a GPU, threads are grouped into hardware clusters called blocks. Instead of forcing everyone to fight over one global top 1,000 list in main memory, you utilize the GPU's ultra-fast shared memory, which is physically located right next to the processing cores.
Okay, so each local block of threads runs its own isolated tournament to find its local top scores.
Exactly. You break the 2 million pixels down into smaller grids. Each grid finds its own winners simultaneously without talking to the other grids.
Wait, but eventually, you still have to figure out who the global winners are. Doesn't merging all those local winners just create another massive bottleneck at the very end?
It would if you merged them all at once. But you do it hierarchically. You take the winners from level 1, pair them up, and run a second set of tournaments. Then a third. It is a logarithmic reduction tree.
Ah, I see.
And algorithms like Bitonic sort are brilliant here because their comparison sequence is strictly predefined. The threads don't need to branch or make complex decisions. They just execute a fixed pattern of compare and swap operations.
Which keeps the hardware perfectly synchronized. You align the flow of the algorithm with the physical layout of the chip itself. That is so elegant.
It really is. But hardware architecture isn't the only constraint that changes the game. There is another massive hardware-level optimization the sources emphasize.
Knowing the bounded value range of the data.
Yes. This scenario really tests your system's thinking. An interviewer gives you the top K prompt, but when you ask about the data, they tell you the values are strictly bounded integers.
So, like, maybe they represent user ages, which max out at, say, 120, or specific network latency metrics strictly capped between 0 and 65,000.
Exactly. If the values are strictly bounded and your first instinct is still to build a heap or a botonic network, you are doing entirely too much work.
You're over-engineering it.
Massively. You don't need to compare elements to each other at all. You can just map them directly into a histogram.
Oh, wow. So you just allocate an array of size 65,000.
Yes. The index of the array corresponds directly to the value, and the content of the array holds the frequency count.
So as you stream through millions of records, you read a value, jump instantly to that index in the array using direct memory access, and just increment the counter.
It is pure O of one insertion per element. You do a single linear pass over the data. Then to find the top K, you just start at index 65,000 and walk backward.
Just walking backward and accumulating your counts until you hit K items, the time complexity drops to O of n plus range.
And in practice, O of n plus range using sequential memory access is staggeringly fast. It absolutely destroys a heap in terms of raw speed. There are no tree rotations, no logarithmic overhead, no recursive stack frames.
It perfectly demonstrates that the most optimal algorithm is often just the one that best exploits the physical constraints of the data itself.
Exactly. It's about knowing your data.
But let's push those constraints even further, because the histogram works beautifully if you have a known, limited range of integers. What happens when the data doesn't have a neat upper bound? And worse, what if the data literally never stops flowing?
Yes, the fire hose era.
Right, because the algorithms we've discussed so far, heaps, partitioning, histograms, they were mostly developed for static data sets sitting obediently in memory or on a disk.
They assume you have all the data right there. But modern engineering often deals with continuous high-velocity streams. Think about aggregating global Twitter interactions or real-time YouTube view counts.
If the stream never ends, how can you possibly keep an exact count of everything without running out of memory? I mean, if the distinct identifiers, like user IDs or video URLs, number in the billions, an array or a tracking table would eventually exhaust all available RAM.
You physically cannot keep an exact frequency count of every single item. It's impossible. And if we connect this to the bigger picture, that realization requires a profound shift in how we define a solution.
So what do? We just give up on being perfectly accurate?
Basically, yes. In high-scale distributed systems, top K rarely means the absolute, mathematically exact top K anymore. We surrender the requirement for perfect accuracy and embrace probabilistic data structures.
Oh, like count-min sketches or heavy keepers.
Yes. Tools like the count-min sketch allow us to find the approximate heavy hitters in a continuous stream using a tiny, strictly capped footprint of memory.
Okay, I have to ask about the count-min sketch. How do you track the frequency of billions of items in a fixed amount of memory without the counts becoming entirely corrupted? I know it loses hashing, but how does the mechanism actually guarantee you don't lose your top items?
It's so clever. It uses a matrix of counters. Imagine a grid, just several rows and columns, and it has distinct hash function for each row.
Okay, a matrix with hash functions.
Right. When a new item arrives in the fire hose, say a specific video ID, the sketch passes that ID through every single hash function. Each function generates a column index for its respective row. The algorithm then simply increments the counter at those specific intersections.
Wait. If you have billions of unique video IDs and only a small matrix, multiple different IDs are inevitably going to hash to the exact same bucket.
Oh, they absolutely will.
They will collide, which means the counter in that bucket will be artificially inflated by completely different videos.
They will collide. That is the deliberate mathematical trade-off. The counts are guaranteed to be overestimates because of the overlapping hash shadows. But the brilliance of the count-min sketch is how it retrieves the count.
How does it untangle the collisions?
When you query a specific video ID, you check all the buckets it hashed to across the different rows. You then take the minimum value among them.
Oh, wow, I see. Because the collisions are functionally random across the different hash functions, it's highly unlikely that a low-frequency item will collide with high-frequency items in every single row.
Exactly.
So by taking the minimum, you essentially filter out the noise of the random collisions.
You've got it. The background noise of low-frequency items creates a sort of baseline floor of collisions. But your heavy hitters, the viral videos appearing millions of times, they will stand out distinctly above that noise floor.
That is brilliant. You get a highly accurate approximation of your true top K elements using maybe a few megabytes of memory while processing a literal infinite stream of data.
And that, right there, is the difference between reciting a textbook answer and doing real engineering,
Yeah.
which loops us perfectly back to you, the listener, sitting in that interview chair.
Yes, because it's funny how the cultural legacy of the top K question has evolved. It used to just be a way to check if someone knew their basic algorithms. Now it has become the ultimate senior engineer filter.
It acts as a filter because a junior candidate hears the prompt and immediately begins writing code on the whiteboard. They are frantically trying to prove they memorize the optimal time complexity.
But a seasoned systems architect responds entirely differently. They halt the process. They map the terrain before committing to a single line of logic. It's really a masterclass in requirement gathering.
Exactly. A strong candidate starts the interview by basically interrogating the interviewer.
Right. They start firing off the winning questions. How big is N? How big is K? Is it streaming? Is it on a GPU? Is this data in memory or on disk?
And they also define the specific performance metrics. They ask, are we optimizing for latency, trying to get the answer as fast as possible for one user? Or are we optimizing for throughput, trying to handle millions of these requests per second on a shared server?
And asking those questions is not stalling. You aren't buying time to remember how a heap works. You are demonstrating that you deeply respect the constraints of the hardware.
You are showing the interviewer that you see the invisible mechanics beneath the prompt. You are evaluating memory bandwidth, CPU caching, hardware parallelism, and probabilistic trade-offs. That level of inquiry is what separates the coders from the architects.
So the core takeaway for you, anyone heading into an interview or even a high-stakes architectural planning meeting, don't be a heap bot.
Please don't be a heap bot.
The moment you hear find the top something, take a breath. Let the junior engineers immediately reach for the standard library sort function. You take a step back and ask about the workload.
Because if you can seamlessly turn an algorithm recital into a deep engineering discussion about warp reductions on a GPU, or histogram-based selection for bounded integers, or the mathematical elegance of a count min sketch for a fire hose of data, you prove your maturity.
You show them you are an architect who builds systems that survive the real world.
You're not just writing code. You're designing reality.
Exactly. And that is how you actually get the job. If this breakdown helped you see the hidden layers in those simple-sounding interview questions, pass these insights along to a friend who is currently grinding LeetCode. Help them break out of that textbook mindset.
Absolutely. And this raises an important, somewhat provocative question to leave you with regarding your own daily work. We just deconstructed a universally accepted perfect textbook algorithm and revealed how it actually collapses under real-world constraints.
The trap of best practices.
Exactly. So look at the architecture you are currently building today. What other unquestioned best practices or standard algorithms in your current tech stack are secretly just hiding under specified constraints?
Ooh, that is an essential question to mull over. You have to evaluate the tools in your hand and the environment you are operating in. Are you out there right now trying to mow a sprawling lawn with a surgical scalpel? Keep questioning those constraints. We'll catch you on the next deep dive.